All right. Thank you so much, everybody joining both live and in the recording. It is my pleasure here to start off our November CS Speaker Series webinar. My name is Mary Bonaparte Soller. I am the Associate Director at the K-12 STEM Center. We do a variety of outreach events in science and engineering for students, for teachers, for families, and this is just one great event that we're here to bring you today. And it is my pleasure to introduce Professor Jesse Thomason. He is an assistant professor of computer science at USC, doing some amazing work in grounded language learning. Just quickly, he was a visiting scholar with Amazon Alexa AI and previously a postdoctoral researcher at the University of Washington. He got his PhD from the University of Texas in Austin. So really excited to hear all about his work with natural language processing and robotics, and gave you the opportunity to get a taste of some really cutting edge research in computer science, some really neat stuff that hopefully you can think about how you could like to bring that back to your classroom and your students. So with that, Jesse, you can go ahead and take it away.
All right. Yeah, thanks so much, Mary. And feel free to stop me anytime if you have some curiosity about something that I've mentioned or want to go deeper into a particular topic. So as Mary mentioned, I just started my lab last year. So I'm a new assistant prof at USC. And while I'm going to be talking generally about natural language processing for robotics, I do want to motivate why we would need a robot to understand language in the first place. And so I've got two examples here. On the left, what you'll see is some work that one of my students did over the summer, not with me, with one of my collaborators at Cornell, on assistive robot feeding. So in this task, a person who has upper mobility impairment of some kind is being fed in the way that a human caretaker would normally assist somebody with this activity of daily living by acquiring a bite of food, and then putting the food near the person. And eventually what needs to happen is the robot needs to drive that food towards the person's mouth to allow them to actually take the bite. Now, this robot doesn't know anything about language, and that's to be expected. But as a consequence, what you'll see in a second is this guy in the blue shirt is going to ask a question to the woman who's in the powered wheelchair. And then when she tries to answer, the robot shoves the food in her face and is like, it's time for you to take a bite now, which is super disruptive to the conversation. It's like if somebody asked us a question and we took a bite at the same time, which does happen to us, and then we have to sort of chew with our mouth full or cover our mouth while we're trying to answer, and it's awkward. So what we'd want from a system like this is for it to process the conversation that is happening, understand things like conversational floor, who is speaking, who is about to speak whenever this person stops, and then have the robot, similar to the way that we sort of sneak bites in between conversational turns whenever we are talking and having lunch at the same time. We want the robot system to basically make those same kinds of inferences and sort of offer the bite at a time that is conversationally appropriate. And to do that, we need the robot to understand natural language. On the right-hand side, you'll see many videos of a robot in a controlled lab setting accomplishing short horizon tasks that involve moving an object from point A to point B. So in the top left, you see, can you move the Coke can to the far counter? So that is, pick up the Coke can, move it to whatever the far counter is. Or after that, there's pick up the jalapeno chips, move it to the trash can. So these very simple, go find this object and then put this object at this location. But we can see that a robot in this scenario is actually accomplishing these tasks. Now, this is from the Google Everyday Robotics Lab, so huge, well-resourced lab at Google that can, throw as much money as they want to at this problem. And at the end of the day, the only thing that robot can do is still pick up the object, move it, and drop it somewhere. So I'd like, as a lab, my goal is to extend these kinds of language capabilities to make robots that are more socially aware, as we see on the left, and more capable, which we see on the right, to do more complex things than this sort of simple object moving around. And if we consider what kinds of robots are commercially available today, it kind of feels like this language technology should sort of have already happened. So we've got systems like, you might have seen demos of Boston Dynamics robots. These tend to make YouTube or make media because they're very flashy. They can dance and they can do acrobatics, but they can't talk. You can't tell them to do something. You have to sort of hand program all of their behavior. The most commercially successful robot, I think, is the Roomba, right? I have a Roomba. I have two Roombas, actually, one mops and one vacuums. And then if the mopping one goes first, it like pushes cat hair all over the place and makes a big gross mess. So I have to get the vacuumed one to schedule itself. With the mop one, it's super tedious, and I have to do it all through the app. And it would be great if I could just walk up to them and be like, vacuum first, then mop. You know, that's what we would do if we were teaching a kid how to do this. But they don't have language capability. They have to be controlled either through an app or just through their own learning in the environment. And then there's this assistive feeding task that I mentioned on the last slide, where if we're doing byte acquisition and sort of trying to augment someone with upper mobility disorder to have sort of more independence at the table, to not have to have an actual person there feeding them, we'd like to give them that independence by providing a robot that understands social cues well enough to not comically shove food in their mouth whenever they're trying to say something, which is what we saw in that last video. And we have systems that are able to understand dialogue currently. So we have things like Cortana and Siri on our phones that we can say like, oh, set an alarm, set a reminder, create a calendar event, send a text message, and it works with an asterisk, right? Like nobody actually uses Siri and Google for the reasons that they only kind of work, right? Mostly they're kind of annoying. But when we look at systems like Amazon Alexa or Google Home, we start getting into the space of like bots that use artificial intelligence and machine learning that can kind of understand language correctly, right? Like people use their Google Home and their Amazon Alexa to place orders, to turn on lights, to play music, and they basically work. And kids are really good at using them. Like kids are good at using Amazon Alexa, and it makes them rude. I don't know if you guys remember this article from last year about kids don't say please anymore because Alexa doesn't understand what they say when they say please. And it feels like we should be able to take the technologies in these systems that do understand language and just like put them on the robot and have the robot start understanding language. And what I'm going to discuss is why this is hard. And it really comes down to the fact that these systems that do understand language mostly do so without needing to understand the visual environment in which they operate. I don't need to know where the lights are to know if the lights are turned on or not, on or off. I don't need to know anything about your kitchen to play music if I'm a device that's sitting in it, right? Where a robot system really needs to understand everything in the visual environment around it. It needs to know who's talking. If it's going to try to shove a bite in somebody's mouth, it needs to know if they're already done chewing, if they're talking right now. The Roomba needs to be able to navigate through your house without running into the dog or running over cat vomit and then dragging it all over the floor, which has also happened in my house. It'd be great if they could use their vision to avoid those problems. So generally, what I work on is enabling robots to perform language grounding, which is connecting language commands to their visual world through interacting with people. So we'll see some highlights of that today that I hope are exciting to go through. So I'll go through two bits in this talk. One is just natural language processing more generally, and hopefully that's something that, at least in the upper division CS, I feel like NLP might be the kind of thing that is covered as like an application area. And if not, maybe it could be. I think it's gotten a lot of like fun commercial applications, especially lately, that are easy and fun to demo. And then we'll focus on natural language processing as it applies to robotics. So we'll start out with just a general discussion of NLP. And I know that some subset of people heard some of this when Professor Jha did his talk in the same series earlier, so I'll limit it a bit. So natural language processing is mostly concerned with turning in the wild human language into something that's machine readable for downstream tasks. So what I mean by that is you can think about applications where we see NLP in our day-to-day life. For example, fake news detection. If you've been on Twitter, at least before this last week when everything caught on fire, they had implemented this new system where if a tweet were like linking out to suspicious sources or like clearly some kind of election misinformation, it'd have a little flag on it that says like, hey, Twitter thinks that this thing might be misinformation. That kind of technology is backed by natural language processing. Even simple stuff that's old, like spam filters in your email, right? You've got your spam folder, you check it every now and then when it accidentally puts something important in there. But for the most part, your spam filter catches like gross emails that you don't need to open that are gibberish. And it does so by running natural language processing classification systems that look at the text and try to decide whether or not this seems like a legitimate email or a gibberish email. And more recently, NLP has been in the spotlight so to speak, because of textual language modeling. So doing things with text generation, you might have heard the term GPT-3, these sort of big models that do forward prediction, where you give them some text and then they give you a lot more text that is a plausible continuation of what you said. At a more sort of banal example, autocomplete on your phone. As you're typing a text message, you might get these little bubbles of like 3 possible words to continue what you've said so far. That is backed by NLP, where we look at big corpora of documents and text on the internet that people have written, and we can use that to build statistical models that say what words are likely to come next, given what you've typed so far. You might have even noticed, depending on what kind of phone you have, that these things will learn from you too, and they'll start suggesting things that you tend to say, which I find a little bit creepy, but it's typically less annoying once it starts learning about you, right? One example that has become really successful is machine translation. So now, not just on Twitter, but on most social media, if there's a post in another language, there's often a button you can click. It's just like, hey, show me like an approximate translation of this. And those are all backed by NLP systems. So I'll go through a quick example of what some of these things look like. So if you're performing sentiment analysis, this is an easier version of fake news detection, where you've got something like tweets coming in and you just want to decide, is this tweet positive? Like, is it somebody who's happy or feeling good, or is it negative, somebody who's feeling sad or feeling down? Twitter and other social media love this kind of task because it drives ads, right? You give different ads to people who are sad and people who are happy. That's the dark reality here. But it does make it a popular task for NLP people to think about. So for each tweet, I know one of my attendees is driving, so maybe we'll have a hard time with the engaging bits here. But if you're able to, the two who are here, give me a sense of whether a tweet feels clearly positive to you or clearly negative. Then we can see if we can do this task, and if we can do it, we can talk about how a natural language processing system would do it. So our first candidate. Happy dog, smiley face, music, emojis, and then some attached video. Think positive or negative tweet. Yes, I see at least one thumbs up. Easy, positive tweet. They're even saying the word happy in here. We got a no longer one. The owner of this shop allows stray dogs in after dark so they can spend the night safely. Heart emoji, prayer emoji. He puts blankets to cover the cold tiles so everyone has a comfortable bed. Such initiatives must be shared. Heart emoji. So this is another easy one, right? Very positive tweet, lots of hearts, lots of happy words. What about you can't handle a pet? You can't even handle a dog. Start off with a pet rock. Positive or negative? Oh, I've got chats too. Are chats where stuff is coming in? Yes, there's some chats. All right, so this latest tweet. You can't even handle a dog. Start off with a pet rock is our beginning of like, maybe this is negative. Seems a little bit meaner. Never met such a dog. I read this one as negative because of the dots. I think generally meeting a dog is negative in this context because it's probably dog as, a person who is a dog as opposed to a dog that's a dog. I think if you meet a dog in person, it's positive. But if you meet a person who's a dog, it's negative, which is some fun polysemy we'll deal with in a second. Or, my God, this is such a dog whistle. Now we're seeing dog used in a third context. We've seen dog now as the animal, dog as the person, and now dog whistle, the compound, which is generally going to be a negative tweet about some political or racial messaging. And finally, hot new tip for folks looking for a canine companion. Get a normal dog without a taste for human flesh, and some attached pic. I'd argue this one is hard to tell if this is positive or negative if we don't know what the attached picture is, because it could be somebody sort of being cheeky about the dog that they're happy with, or it could be somebody who is posting a warning, like don't get an aggressive dog. However we do this, we need to know what the word dog can mean. And it turns out this is a particularly tricky bit for natural language processing models. So when we think about what a written word means, if we were trying to look up a word that we'd never seen before, the thing that we would tell kids to do is probably look it up on the internet. The thing that we would have done is look it up in the dictionary. The dictionary is now the internet. So dog, if we look it up on Google, is a domesticated carnivorous mammal that typically has a long snout and acute sense of smell, non-retractable claws, and a barking, howling, or whining voice. That is a lot of words. And if we're a system who doesn't even know what dog means, we probably don't know what the word domesticated means. So there are two problems here. The first is polysemy. Dog has multiple meanings, right? We established in our tweets that we've got both animal dogs and also this second definition of an unpleasant, contemptible, or wicked man. And dog is also defined by a bunch of words, and we need to know what all of those words mean to be able to figure out how dog is being used in context. And so if we follow a path and we say, well, I'll just look up every word I don't know, then if I look up the word domesticated, I'll get tame and kept as a pet or on a farm. And then if I have to look up the word tame, I'll get not dangerous or frightened of people, domesticated. So the word tame has domesticated in its definition. The word domesticated has the word tame in its definition. It's pretty clear. For most words, you'll find a cycle like this quickly. For all words, you will find cycles, because if we define words in terms of words, words are all we'll have. So we need something to connect words together and create a sort of structure. And what the general idea of natural language processing models today is this quote from a psycholinguistics person in 1957, you shall know a word by the company it keeps, which is simply the idea that if we have enough data and we look at enough times that words like dog occur and look at the words that occur around them, we can get a sense of what the word means by just how it's used in context. This is also reasonable, right? This is what we tell kids. If you can't figure out what a word means and you don't have a dictionary, at least way back in the past when we weren't carrying phones around, you just try to figure it out, suss it out from the context of the sentence, what this word probably is functioning to do. So modern models use a notion of distributional semantics, which is just to say, looking at how words occur in a distribution around a particular word to define what the word like dog would mean. And what this means is that the meaning of dog is a learned sort of compact representation of all the neighboring words and sentences where it appears. So we define dog now as our like kind of fuzzy dictionary definition, where instead of actually having a definition, we just have dog tends to occur next to words like bone and play and good and boy, right? So the meaning of dog is still based on other words. It's just a little bit less interpretable if we do it this way. And this is what most modern NLP systems will do to learn their new words. It also means we can catch the multiple meanings of a word by looking at the surroundings. So now if we're talking about like a person who is a dog, we'll have words like wicked or, you know, ragged or gambling around it, where if we have dog, the animal will be stuck with, you know, good boy. So if we return to our sentiment analysis and we're trying to decide if tweets are positive or negative, bearing in mind that we now have this method of representing words as combinations of other words, then we can start to imagine what the machine learning model that does this task is doing, which is associating certain features of words with things that are positive or negative. So happy dog. Here, the word happy obviously is a word that indicates positive sentiment, but we can determine that by looking at lots of tweets that are happy tweets and seeing that the word happy actually shows up in them, and then looking at all the other words that show up. So dog is occurring here next to happy, and that will let us know that the word dog might itself be enough to indicate that a tweet is positive. If we look at our second example, we had stray dogs occurring next to words like safely and comfortable. And so again, this is evidence that maybe dogs are just positive in general for people. I think that's probably true. If you just looked at all the tweets that involve dogs, most of them would be positive. If we get to our negative example, you can't handle even a dog, start off with a pet rock. We've got dog, it's next to pet now, so we still know which kind of dog we're talking about, but this is a negative tweet because it's being, you know, mean to somebody. Never met such a dog, and now we're talking about the sort of wicked version of this word. And it's tough to tell that this is a negative tweet. I'd say once again that it probably is because of this 2 dots bit, which indicates sort of some kind of extra textual information about the tweet, that someone's sort of looking askance as they say it. Or, my God, this is such a dog whistle. And now we've got dog whistle, which is a compound form that we know is negative. But when we get down to our final sort of difficult tweet, this hot new tip for folks looking for canine companion, get a normal dog without a taste for human flesh. I'd argue that we actually need the picture to tell whether this is a positive or a negative tweet. So even if we know what all of these words mean, we really need to understand the underlying intent of the person. And so if this is our attached picture, which is this like frightening growling dog, versus this happy dog with a little butterfly on its nose, then the sentiment of the tweet is quite different, right? And if you extrapolate this to something like a spam detection system in your email, being able to see like what the attachment is a lot of what a spam filter is doing. So it's going past text and saying like, hey, is this actually an attached PDF or is this an attached rootkit or like computer virus, right? It tells you a lot about whether an email is spam. So again, NLP is concerned with turning in the wild language into something machine readable. And we just went through an example of sentiment analysis, but I want to give another example where this is the case for autocomplete on your phone specifically. So I gave this example that when you're typing, your phone can give you suggestions for what the next word would be. So if I'm typing to somebody and I say, oh, I'm so excited to show you the new something. So you're a person who's writing autocomplete software. And if you're given this text, I'm excited to show you the new blank. There's a lot of possible words you can suggest, right? You could probably come up with just about any noun here. So if I also give you the swipe, so I know like at least one person can see these slides. So here's our swipe pattern. So like the person is swiping across the keyboard and they do this. Can we come up with plausible words from this swipe? Car. Car is definitely a plausible word from this swipe. It might be the first one on my list. Yes. Any more? I came up with 4. I don't expect anybody else to come up with 4 because I had to, squint at it for a while, but. Cat. I think cat is totally reasonable, but it's not in my list. I'm so sorry. The other ones I came up with were czar, because we sort of zoom by that Z. Cart, because we have to pass the R and we're ending close to the T, and case, because it's unclear whether we're trying to catch that S in our last little curve. So now, if we're autocomplete software, we want to offer, the top 3 possible words. We've got 4, maybe 5 if we throw cat in there. So which ones do we offer? I'd say we don't have enough information, right? If we had the dialogue history, maybe if we know something about these people and we've seen what they're talking about in the past, we could get some more information. And maybe that past information isn't helpful, right? So here I've just got some past exchange where they were not talking about anything substantial. What we really might want is if we know there's an attached photo, then we could look at the photo and then determine what word is missing here. So for example, if this is our photo, it's now unambiguously clear that car is our word, right? Now, if it's this photo, maybe we're talking about the new cart. Maybe these are some team working on a go-kart race. Big stack of papers, excited to show you the new case. Or a bottle of czar tequila, excited to show you the new czar. So do tech companies actually use this kind of multimodal attached photo information for autocomplete whenever you're running stuff on your phone? I don't know. I don't think so, but it seems totally plausible to me that they can or should. So next time you're texting and noticing autocomplete, see if you can tell whether it's using the photos in the conversation or not. I'm genuinely curious if companies do this. So we've looked now just briefly at autocomplete on your phone. The last little bit I want to talk about for NLP that is going to be our segue into translating these applications into robotics is machine translation. Because machine translation has been so successful, when I started my deep dive into CS as a late high school student and then early undergraduate, machine translation was a silly problem almost. It was people had worked on it for so long and they had tried all these different methods and it just wasn't very good in 2013, 2014. It was still a really, broken application. And now it's so good. You can basically tell what's happening in a tweet or in a Facebook post in any language by clicking the translation button and getting a sense of it, right? You can tell it's a little bit off, but the semantic content is all preserved. So it's awesome. And the way that it works is if I have an input sentence like 2 trees sway, the computer sees these basically as just numbers. It's got a number that represents, hey, I'm starting a new sentence, a number that represents 2, a number that represents trees, a number that represents sway, and a number that represents now the sentence is over. And it's going to feed those into what's called an embedding, which gives us this compact vector of real numbers that represents the word to the machine. And these word vectors, is what we call them, are the representation I was talking about earlier in the talk, where we have this notion of knowing what a word means by the company it keeps. We can basically look at a large volume of documents and get this compact representation that says, you know, dog is really similar to cat, except that dog shows up more in happy things and cat shows up more in ambiguously mean things. And so we can get synonyms, we can get word similarity. And what we do is we feed those words one by one into a specialized machine learned model whose goal is to capture the entire meaning of the sentence by reading in all of the words. So this system runs through, it reads, start a sentence, two, trees, sway, now the sentence is over. And in the end, it will have a compact, again, just real number representation of this sentence. So some high dimensional, maybe 128 to 1,000 dimensional vector of real numbers that is meant to encapsulate the entire meaning of the sentence. It's a big ask, but it turns out if you have that dimensionality high enough and you have enough data to learn these models with, you can do a pretty decent job. And so what will happen is we'll take that latent representation of the sentence that we've learned, and we'll give it to another model to do the machine translation that is trained not for English, but for the target language that we'd like to translate into. So in this example, we're going to go from English to Arabic. So we have a separate model that's trained in all the same ways. So it's got its own representations for, oh, here's all the Arabic words. Here's my compact representation of each Arabic word based on the company that it keeps and the corpora that I have. And I'll learn how to go from my latent representation of English to this target language. If you have any like memory of notions of this from linguistics, this is sometimes called the interlingua, some sort of idea of a universal substrate of what something means as we go between languages. This is sort of what these vectors that are happening in the middle are meant to achieve, but it's a tall order to actually claim that they are an interlingua. I think that they are not, because otherwise the translations would be perfect. But the upshot is, we now have a decoder model that takes in this encoded representation of English and produces one word at a time the target words in the target language. So in this case, Arabic. So we've got shajaratan, which is two trees. It's this word for tree, and then this special case for there being exactly two of them, which English doesn't have, but Arabic does, the dual case. And then tatamayalan, which is sway, agreeing with there being two things. So we've got subject-verb agreement as well. This is a brief illustration of the same idea. This is going from Je suis étudiant. I do not speak French even a little bit, so I'm definitely mispronouncing all these words. So this is going from French to English to say I am a student. And I only bring this particular animation up because I want to re-emphasize a point, which is that at every step of predicting what word comes next in machine translation, we only need to consider the words of the input. So the words in English, or on this slide, the words in French, and then the words that we've produced so far. So again, every word we predict is only conditioned on the new information that we've given ourselves by predicting words in the past. So there's nothing happening as we do the translation. It's not like we're talking to somebody to do it. We get to make the whole plan all on our own. And that's very different than what happens when we try to apply things like machine translation to robots. So if you recall this video from before, this is our robot responding to natural language commands like, can you move the Coke can to the far counter, with behavior. So you can imagine framing this as a machine translation problem. We could say, can you move the Coke can to the far counter, and try to translate that to target language, look down, rotate right, move forward, rotate right, grasp the Coke can, and actually go to not Arabic in this case, but robot language, where the robot language is the behavior that you want the robot to execute in the real world. And this is tough because if we use this same architecture, we can have our encoding that tries to create a latent representation of the English command. Here, can you move the Coke can to the far counter? But when we move into our target language of robot actions, if we first predict you should look down, and then we're supposed to next predict that you should rotate right, and then you're supposed to go find the Coke can. these predictions of like looking down and rotating right are very specific to the starting position of the robot and to the kitchen that we're operating in. So if you imagine I'm standing at this desk and someone tells me walk towards the door, I'll turn right and I'll walk out. You can't see my door, but it's over here. Where if I were even standing at a slightly different part of my office, like here, and someone told me walk out the door, well, then I'd turn right, and I'd move forward, and then I'd turn right again, and then I'd go to the door. So the sequence is actually different, even if I'm standing in a different space. So the same instruction in a different kitchen or a different robot position will need different actions. So we really need the robot to be using its camera. It's gibberish to ask it to do this without its camera. And second, every time we make a prediction like, hey, you should look down or you should rotate right, what we're seeing in the world will change. So what we decide to do in our decoding process actually affects the world. It affects what we're doing, and it might affect other people if we're picking things up or saying things. So we have to move to a different paradigm. So just as a quick recap, we've looked now at positive and negative sentiment classification on Twitter, at next word prediction for swiping words on your phone, and for machine translation. And in all these cases, it was the case that having a little bit of extra information from vision, either in the form of attached images in your tweets or attached photos in autocomplete, or in the case of a robot, really needing the whole camera input, we needed more than just words to do this task well, which will bring us to the second half of this talk, natural language processing with robots. Before I do that, move on, because we've been talking about NLP for so long, I do want to pause in case people have any questions or want to hear a little bit more about any of these topics. Also, let me know if this is very boring so that I can pivot and talk about something slightly different. Any thoughts so far? All right. So let's deep dive then on this problem of not being able to go straight from English to robot action. It turns out this is really tough. This is the primary thing that my lab is focused on. And so when we move into language with robotics, there's a couple ways we can frame the problem. And I think the easiest one to think about is this notion of like, I give the robot some instructions in English and I want it to actually do what I said. So there's a way of benchmarking this kind of capability that is popular in the field right now called vision and language navigation, which is exactly this task. I give an instruction like, leave the bedroom into the kitchen, walk forward, take a left at the couch, stop in front of the window. And I want a robot agent to respond by actually moving through my house and doing this task. And you can imagine this is a component of a lot of different stuff. What I think of is when I look at my Roomba and I want the Roomba to clean a very particular part of the house, I would love to be able to tell it that instead of opening the app and drawing zones where I don't want it to go to try to feed it into the location where I'd like it to be, or picking it up and dropping it there and hoping it stays and does the job I want it to do. Never does. It always just drives off to do whatever it was going to do in the first place. So being able to tell the robot what to do and have it actually do it is a huge ask. This will be decades of research to get this working well, but we're making progress. And so the way that people benchmark these today is by doing it fully in simulation. So rather than actually running a robot, what they do is they have gone through and captured houses. So what you're seeing on the left, this GIF that's playing, is actually a series of panoramic images where someone has taken a 3D panoramic camera and put it in a bunch of different locations in a house. So on the right, you see a sort of top-down view of a house exploded out, and each of the blue dots in that is a place where the camera was put down on this little tripod, and it captured a 3D view of everything around it. And as a consequence, we can simulate what it would be like for a system to move through that house by having it move from these different camera positions and see this very nice 3D version of like what the house looks like from that position. And what we want to do is take our source language, again, which is going to be instructions in English, and translate that into our target language output, which is robot actions. And in this simple world, all the robot can do is rotate left, rotate right, move forward, or stop and say that it's accomplished the goal. And the way to approach this is very similar to what we saw with machine translation. If we've got our instruction like move inside and stop in front of the formal dining table, then we can translate that into some latent representation of all of the English, and then we want to decode it action by action into what the robot should do. And all we have to change is every time we predict an action, like rotate right or move forward, we have to give the camera input instead of the previous word that we predicted. So we can get the camera stream and then make these predictions one by one. So to illustrate that a little bit in a higher resolution, if our instruction again is move inside and stop in front of the formal dining table, then our English instruction will run through this learned network and we'll get our little interlingua that is meant to represent all of English in this tiny little compact vector. And we'll decode that into the target language, which is now robot actions. But we will add input from the robot's camera. So if I'm currently standing on the patio and I can see the house in front of me and the door is like off to my right a little bit, then we can predict that the first thing I should do to move inside is to rotate right. Then I'll get a new input from my camera, which is now the door is dead ahead of me. So what I should do now is move forward, right? And I'll keep moving forward till I go through the door. I will have then accomplished move inside. Now I've got to find the formal dining table, go find it and stop in front of it. So this becomes a plausible ask now of the machine learning model if we have camera input. And so I know there are only two of you. So if are y'all, oh, actually there might be another person. I see him in the waiting room. So we will try this exercise. There is a way to see what it's like to try to solve this task as a person that I will have y'all attempt. So on the left, you can see an interface where a person is playing the role of the robot. So they're sort of dragging the screen around and moving through a house. You move through the house by clicking and dragging and then like right clicking on these little cylinders to move. And the goal in this video that's playing is to find a room with a mat. So you imagine a Roomba, somebody has told you go clean the room with the mat. That's not quite enough information to figure out where you're supposed to go. So in this case, you can ask your partner, who is meant to be the person who's guiding you, should I go into the hall or into the office? On the right-hand side, you see somebody answering that question. Should we go left into the hall, follow it to a living room? They send that message back, and now the robot, the person playing the role of the robot, retakes control and has to start moving around. And so this is a turn-based game where we simulate the role of robot trying to follow a language instruction and person tediously trying to give a robot a language instruction and coming to terms with all of the, even at human level, all of the difficulty of specifying a path. One thing I also want to point out is when a question is asked, the person playing the role of the instruction giver will be able to see what the best next steps are. So you see on the right-hand side now at the bottom, there's this new video that show best route that basically shows like if your robot were perfect, this is what it would do next. And their goal is to describe that route back to their partner, right? So here they're saying, oh, what you need to do is go up the stairs. Does that all make sense so far? If it does, then I have this little activity that we'll try. And if even one person is able to play it, that'll be awesome. There are, I think, 3 participants and me, which would mean that we have an even number total, which would mean we could have 2 games playing. The general idea here is if we're going to ask a computer to do it, we should be able to do it too. So if you navigate to this link and then click 2-player demo and then scroll to the bottom of that page and click start task, then it will pair us to play this little game. And I will play it also, which will mean that I am able to show on the screen with whoever I get paired with what the task looks like. And we can see just how frustrating what we're asking robots to do can be. So this is the link, cvdn.dev, if you're not able to click. So really short little URL. And then 2-player demo, and then start task. And then if any one of you is able to do this, it'll load up. Oh, thank you, Mary, for putting the link.
Sure.
Oh, here we go. Here's somebody. So the goal room contains a vase. I appear to be the navigator, so I am the robot. So I have to look around, decide if this little laundry room looks like a place where a vase would be. I think not. Where are we? We're in a destroyed basement. Will the room with the vase be over here? Probably not. Oh, but we don't have any choice. We can't go upstairs, we're a robot. So we start moving. We got a little option here. We go down the hallway towards what looks like a living room or over here to a bedroom. So we can ask our partner, whether we should go down the hallway or into this room on our right. So if you imagine this in the context of an actual Roomba, for example, this would be, I tell the Roomba, hey, go clean the room that has the vase in it. The Roomba starts driving, and when it gets to a juncture and it's not sure how to get where I'm asking it, it can ask me, send me a text message, say, oh, which way was I supposed to go, by using its camera, and then I type back to it. And so I think one of you is probably the partner if you're able to view the next thing. Oh, room on the right, yes. So I get my little instruction. I should go to the room on the right. Are we sure? There's nothing in here. And so you see the general complication of the task, which is it's hard to get robots to do this in the first place. It's even hard to get people to do it well. And so we end up with this very tricky sort of data to work with. Let me see. Oh, I lost my screen share a bit. So if we think about how we would go about actually modeling this task, then we've got this setup where we've got a navigator who's the robot, and then this oracle who is the person who is telling the robot what to do. So we've got, here's our example from the demo video where the navigator moves around a little bit and then asks this question, should I go into the hall or the office? Oracle says, oh, go left into the hall, follow it to the living room, and then the dialogue continues. And so if we think about modeling this, what we'd really like to do is be able to build natural language processing systems that can play the role of either navigator or oracle. And what the navigator needs to do is both follow instructions, so move around the house, as well as ask questions. And what the oracle needs to be able to do is answer those questions, right? So given what the person asked, look at the route that needs to be followed and then produce language that corresponds to that route. And the way that we do this, if we want to think about some fun sort of theory of mind modeling, is if we're answering a question, what we want to do is consider if I were to say, so let's even use the example we just saw. So my partner, one of you, said it's the room on the right. And if we imagine, if I generate room on the right, what do I think that my partner will do? So if we ran that simulation, what we actually saw is I looked in the room on the right, I couldn't find any more like pylons to walk to, and I got confused. If we had generated a different answer that said, say, oh, turn to your left and go down the hall, then it's the room on the right. Then we can imagine the person might have turned and gone down the hall and followed. And so we can try to pick the answer that we think will cause our partner to do the right thing. And this is basically what we do in regular conversation, right? Like we say a thing that we think will cause the person we're talking to believe what we believe or do what we want them to do. If you frame all of communication as some terrible manipulation game, this is basically how we talk, right? And so we pick the answer that we think will cause our partner to do the navigation that we want them to do. And conversely, if we are asking someone a question, if we are now playing the role of the robot who's trying to do navigation and we get lost, then we consider, if I ask this question I'm thinking of, for example, should I go down the hall or should I go into this room on the right? I'll imagine what my partner could think about saying back to me. So they could think, oh, I should say room on the right, or I should say go down the hall. If I say just, oh, which way do I go now? Maybe they have a lot more answers they have to say. If I ask something really simple, like, do I go to the room on the right? They might just be able to say yes or no. So you think about how your question influences the space of answers your partner can give you. Knowing that what your partner is going to do is think about the answers that they can give you and what that will cause you to do in response. So you get this two-layer jump now of what I will say will affect what you will say, which will affect what I will do. And so we can search over that entire space and pick the question that we think will cause you to pick the answer that will cause me to do the right thing. And so once again, this is probably not how actual people talk. This is moon man logic. But if we imagine that conversation is just about manipulating other people's intents and goals, this is roughly what we do, right? If we're trying to get somebody to give us a particular piece of information, we ask a question that will constrain their answers to tell us what we're trying to find out. So we call this a recursive mental model, and this is our sort of theory of mind intuition for getting these robots to drive around. So we've done this both in this like fully simulation environment, but also in a physical environment where we actually have a robot car that drives around. So here on the left, you can see a robot car who is saying things like, oh, I have got green walls on my right and there's a yellow corner ahead, and I'm not sure what I'm supposed to do next. So the oracle, who is a person watching the car drive, gives instructions like you need to turn a little bit to the right before the green walls and then stop before you get to the red walls. And then we turn control back over to the car, who continues driving, trying to find the goal in the maze. The last bit I want to touch on is about going beyond the robot's camera, just because robot is actually more than a camera, right? It's an entire sensory system, just like a person. So we have more than just vision. We can look at things and get things like their color and their shape, or maybe some deep visual features from them, but we can also interact with objects. So if I am trying to understand, for example, something about this water bottle, and I put it on the table and I push it, you can probably hear that through my speakers. So I push it, you can hear it scraping across the table. If I am looking at it while I do so, you can also see my arm as I push it will feel some resistance. If it's very, very heavy, I'll feel a lot of resistance in my shoulder and elbow. And so what we can do on a robot system is actually capture those features. We can capture the resistance that the robot is feeling in its joints, as well as the sound as it performs different behaviors on an object. So we can press from above, we can grasp things, we can lift and lower them, and we can even from a small safe height drop them, which makes a really loud sound if the thing is big and heavy, right? And if we do that, we can learn properties of objects as a robot system and tie them to particular words. So I can learn that, for example, this water bottle is full. We can't tell that it's full by looking, right? You probably just on the camera can't tell, but if you hear me drop it again, you can tell that it's full. You can even hear the reverberation of the metal as the water sloshes around. And so this is an example from my PhD days that I'm still very excited about. So I want my students to work more in this direction, about a robot system that learns live what a new word means by tying that new word to sensory perception. So I'll be quiet while the dialogue is playing, but I will interject to mention whenever something interesting is happening. So the robot asks what I should do, and then I'm going to go up and give it a command. So this is, once again, sort of our Google example of we're trying to get an object to go from point A to point B. This is sort of the classic thing in robotics. But mine will be described with these properties: rattling container, which does not describe a unique object the way that all of the examples we've seen so far do, right? If I say the Coke can, I unambiguously can tell which thing is a Coke can. If I say bag of jalapeno chips, I can see it's the bag of jalapeno chips. But rattling container means I need the system to understand what the word rattling means, the sort of sound that an object makes. And so the first thing the robot asks is rattling a property of an object, because it's trying to figure out like, oh, do I have to learn something new now? So I say yes. The robot hasn't heard the word rattling before, but it has heard empty. So the first thing it's going to try to do is cheat and say like, is rattling and empty the same thing? So again, this is, if we go back to the beginning of the talk, I mentioned that we are doing this notion of learning a word by the company it keeps. And so the word rattling and the word empty, it turns out, correspond to a bunch of the same linguistic space, because they are both words about a sound property of an object and about the sort of interior properties of an object. So it's reasonable to think like, oh, maybe these are synonyms. You can imagine if I said, bring me the claret ball, it might say, oh, does claret mean the same thing as purple? These seem really similar in word embedding space. And I would say yes, and then it doesn't have to learn claret at all. But rattling does not mean the same thing as empty, and so it's got a learning task at hand. So the robot lets me know that it's still learning, so it has to do something new. And it asks for an example of something that rattles. So I look at the object sort of in the room, and I find this pill jar that you can't hear it because there's no audio, but the pill jar is full of pills, and it does in fact rattle when you shake it. It's a bottle of Zyrtec, actually, because this is all shot in Texas, where we all have hay fever every winter from the cedar. So now it's for something that doesn't rattle, so it can get a sense of what are objects that rattle, what are objects that don't rattle, so it can get a sense of what this word is indicating in the space of sounds and feelings and sights that it has for objects. So I show it this empty water bottle, which does not, in fact, rattle. And then it wants one more example. So I sort of play around and I find that this jar of country crock is full of coffee beans, actually, because we wanted it to weigh about the same as it did when it had butter in it. But you can't keep butter in a lab for 6 months, so it's coffee beans instead. So that one rattles. So with these two examples, the robot is like, all right, thanks, now back to business. It's gonna start asking me about where it can find this rattling container. But what's happened under the hood is interesting. So it's explored a bunch of objects by doing these behaviors I described earlier, like pushing them around and picking them up and dropping them. And so when I start saying, you know, this word, this bottle rattles, this jar rattles, this bottle over here does not rattle, what happens is we use a machine learning model to isolate what is different about the pill jar and the jar of country crock versus this water bottle. And the key thing that's different, because that pill jar and the country crock are quite different from each other, the key difference is that when you drop them, they make a different sound. So there's this high-pitched like shh sound whenever you drop the pill bottle, whenever you drop the country crock. That doesn't happen with the bottle. And so the model actually learns like, oh, okay, rattling corresponds to this like spike in my audio signal whenever I drop something that's this high-pitched sound. So bear that in mind, because later it will use it to identify the right object. So these are all the things my Roomba doesn't do now. I'm telling it where I want it to go, and it's making sure it understands me, and then it's going to actually do it. So off it goes. One fun thing here is this is a tracking shot. This is underappreciated, but we got all of this in one continuous take. We've got the camera on a little dolly that we're following the robot around on. Not a proper dolly, you know, office chair, but. And so we arrive. The robot looks at these objects. It's seen them before. It's played with them. You know, it's done this like push, grab, lift, drop behavior on all of them. And so it sees these, it remembers its experience when playing with each of them, and then it picks which one makes this high-pitched like shh sound whenever dropped. And the thing that is best matching is this pepper grinder. So it grabs this jar full of pepper corns. If there were sound you can hear even as it picks it up, there's like a rattling noise as it moves it into position. And so it will drive this rattling container over to the final destination office and do a handoff. And so finally, we arrive to Bob, and Bob takes this rattling container. And that is a lot of work to deliver a jar of pepper to your friend for lunch, but this is the future our robots might enable. So just to quickly recap, we've talked about trying to connect robots and language, and the primary reason for that is that while robots keep getting more competent, they tend not to actually be entering homes. They tend not to actually be occupying human space. And a big reason for that is that they are not capable of communicating in the same way that we do. And our primary means of communication is language. So no matter how complicated Boston Dynamics robots get, and no matter how fancy their TikTok dances are, they're not going to be in my house if I can't tell them to go away. my Roomba is in my house, but it does a bad job and I have to use a buggy app to deal with it. And I would really like to be able to tell it, you're not on a cliff, you're just where the carpet meets the floor. Like, it's okay, you can just keep going. But the real impact here, jokes aside, is we would like to get to a point where we can use socially assistive robotics, like things like bite acquisition, to help people who need robots or could use robots to achieve more independence in a way where the robot actually understands the language that they use, understands social construct of things happening around them, and doesn't do embarrassing things like shoving food in their face when somebody just asks them a question. And while we have technology for understanding language in disembodied contexts, like just the assistant on your phone or the thing that sits on your counter, those things don't have to deal with the visual world. And so moving language technology onto robots will require a reckoning of connecting language to vision, which is why we went through these examples of even classifying tweets. Having the visual picture can let you know whether the tweet is positive or negative. Knowing what is attached to a message can help us do prediction for autocomplete. Doing machine translation for going from English to robot behavior requires us to consider the camera. And so we must reckon with the fact that language needs to have visual grounding in order for us to move these technologies onto robot systems. And what I'm trying to do in my lab, once again, is enable these things in a way that actually causes positive social change, especially here on the left, when we have this Canova robot doing the bite acquisition and feeding this person. What we would like to see, and what one of my students is hopefully going to start working on soon, is some kind of conversational modeling where we can tell that someone is about to give up the floor, they're not currently speaking, they're not going to speak soon. And we can do those things if we use natural language processing and cameras to look at who is talking and what they're saying, so that we can time this bite in a way that is socially acceptable. On the right, we'd like to move beyond two things. One, this very simple, like pick up a single object and move it to a single location. But we'd also like to be able to say things like, rather than pick up the jalapeno chips, we should be able to say, grab the bag with crisps in it. Like, get the empty Coke can versus the full Coke can. Get the apple versus the banana. And to have the system go beyond just its visual inputs to understand things like, oh, the apple doesn't yield as much when I squeeze it as the banana does. This is one of the ways I can tell the difference. Or even if we're looking for like ripe banana versus overripe banana, if they're both yellow, the yield and the gripper can tell us a lot of information about them. If I'm getting the full bottle versus the empty bottle, being able to pick it up and actually tell whether it still has liquid in it is the only way to tell for something like this that's fully metallic. So hopefully that's a good overview of the lab, and this has been something that you get a little bit of information out of. I'm also happy to take questions for those who are still around. So thanks a lot for your time.
Thank you so much, Jesse. Ruben, I know you joined in a little late, but any questions for Professor Thomason? Feel free to unmute or enter in the chat.
No, I thought this was great. Sorry, I had so many other meetings and things happening at the school district, and I'm still in transit, so I'm not even home yet.
No
but
worries.
I appreciate what I saw there, and I'll look forward to knowing more later. So thank you again.
Yeah, thanks, Ruben. Thanks for coming.
Appreciate it.
And we will have the recording for you, Ruben, so you can go back and watch the first part. We'll send that to you via email. Jesse, I did have a question.
Sure.
So when you were talking towards the beginning of the talk a lot about, the different models of language and the different steps it takes, it sounded very similar to teaching a child how to speak, or even an adult learning a new language, right? So was a lot of this work based on like linguist work, and like were there, was there work between computer scientists and linguists in trying to develop these models?
So a chunk of work in the space of language acquisition, especially in early language grounding, is based on like cognitively plausible or cognitive behavior for language acquisition. My work tends not to be. I prefer finding the right tool for the final task as opposed to it being sort of inspired by or plausible for child learning. But it is often a helpful way to think about the framing of these problems, I think, especially when we talk about things like acquiring a new word. like, is a model doing something similar to a child where it sees a new word and looks at the context and tries to figure out what the word means? Probably. And it's maybe not that that's just like the strictly most cognitively plausible thing to do. I think it's also what makes sense from an information theoretical standpoint, right? If you're missing some information, you try to use the information around it to infer what's missing. So it's more of a happenstance than an inspiration than a direct correlate. Does that make sense?
Yeah, interesting. Great. And then just from your videos that you were showing of that robot in your lab, so was the robot actually speaking?
Yes, it's great. With the audio, you can hear its horrible robot voice saying, "Okay, now back to business." You'll also notice it does this weird little arm bob, which is actually our way of indicating that the microphone is on. So when the arm is bobbing, it means it's actually listening to you. And then when the arm stops bobbing, it's actually not listening, it's only speaking. And when it's speaking, it can't listen or it'll confuse itself.
Yeah, that makes sense. Oh, neat. That's very cool. Awesome. Thank you. Well, to wrap up, I wanted to share some notifications, some news that are up and coming for teachers who might be interested. But thank you so much, Professor Thomason. I learned a lot. It was really interesting to hear all about this great work with natural language processing and robotics. So thank you so much for taking the time to come share about your work. I know a lot of teachers are going to find it really interesting. So let me quickly share my screen. And I just wanted to announce on behalf of LACO, LA County Office of Education, there's an upcoming free online course that will be taking place January, February 2023 on strategies for effective and inclusive CS teaching. So more information to come, but the link right there to register is available. And the registration will be released soon. It isn't open just yet, but something to look out for. Also, the USC Viterbi K-12 STEM Center has the CS Ed Week celebration coming up in December. So December 5th through 9th, we'll have intro to Python workshops for students. We'll have a code.org teacher training info session for teachers who are interested in maybe doing a code.org professional development series. And a computer science careers panel. So more to come with that. Check us out on our social medias where we'll be posting the activities and events that are going to be available to students and teachers. So keep an eye out for that. And then, of course, we have our next CS Speaker Series session coming up in January with Professor Fei Qian talking about robot locomotion. So if you're really into robots, stemming off from this great talk with Professor Thomason, this is one that will be also very interesting and one that you don't want to miss. So keep an eye out for that as well. And I will stop sharing here. And again, I want to thank you so much, Professor Thomason, for your great talk. I know I really enjoyed it. And thank you to the teachers who were able to jump in for a bit to engage and participate. We appreciate you as well.
Yeah, thanks so much for having me.